You've probably heard the number your whole life. The Milky Way, a glittering pinwheel about 100,000 light-years across, packed with hundreds of billions of stars, maybe a trillion suns, spinning around a common center. It's the size of home, the figure we teach children and print in textbooks, and almost nobody stops to question it. But not long ago, a team sifting through the data from a single European spacecraft, one built to map the sky with brutal precision, noticed something at the galaxy's outer edge. The stars out there were doing something they were never supposed to do, something that quietly broke the picture we'd all agreed on. I'm not going to tell you yet what they saw, or what it means for how big our galaxy truly is. But to feel why one quiet measurement shook a century of certainty, you first have to see just how colossal we were told our galaxy really is. The number we trust. So picture the textbook version. A flattened disk of stars, roughly 100,000 light-years from edge to edge, so wide that light itself, moving at 300,000 kilometers a second, needs 1,000 centuries just to cross it. Our Sun sits about 26,000 light-years from the center, one modest star among a crowd nobody can fully count. The estimates land somewhere between 100 and 400 billion stars, and when you add up all that matter, the total mass climbs toward 1 trillion times the mass of our Sun. It's a portrait of staggering scale, confident down to the decimal, the kind of number that feels settled. Yet every confident number in that portrait began as a guess, made by people who couldn't even see the shape they were trying to measure. A band of milk. Long before anyone spoke of light years, there was just that pale river overhead. Every culture that looked up gave it a story. The Greeks saw spilled milk from a goddess and gave us the word galaxy, from Gala. Others saw a road for the dead, a seam in the sky, a smear of ash from a celestial fire. The idea that it might be something physical came slowly. A few thinkers in the ancient world wondered aloud whether that glow was really countless faint stars, too dim and too crowded to tell apart. But it stayed a hunch, unprovable, competing with myth and with the notion that it was some vapor high in Earth's own atmosphere. For a very long time, nobody could settle it, and the size of that band was anyone's imagination. Those guesses stayed guesses for centuries, until one man pointed a new instrument at that faint band and saw it dissolve into something no one expected. Galileo's stars. In 1609, Galileo Galilei turned his new telescope toward that pale band and looked closer than anyone ever had. Where his eyes saw a smudge, the glass showed something else entirely. The milk broke apart into points of light, star after star after star, so many that he couldn't begin to count them. He wrote that the galaxy was nothing but a mass of innumerable stars gathered together in clusters. Centuries of guessing about vapor and myth dissolved in a single night at the eyepiece. The band wasn't a substance at all. It was distance, thousands upon thousands of suns packed so tight and so far that they blurred into a glow. But the telescope answered one question and opened a harder one. Galileo could see the stars were there, yet he had no way to tell how near or far any of them sat, or how they were laid out in space. Knowing the band was made of stars only sharpened the real problem, because now someone had to figure out what shape those stars formed. Counting the sky. That someone arrived more than 150 years later. William Herschel, a musician turned astronomer, built the finest telescopes of his age by hand and pointed them at the sky with a simple, stubborn idea. If he couldn't measure distance directly, he could count. He called it stargazing. Herschel divided the sky into more than 600 small regions and counted every star he could see in each one, direction by direction, patch by patch. Where the counts ran high, he reasoned, the galaxy stretched far. Where they thinned out, its edge lay close. He assumed his telescope could reach the very boundary of the star system and that the stars were spread out evenly, so more stars meant more depth. Night after night, he and his sister Caroline logged the numbers. Herschel's counting produced the first real map of our galaxy, but the very light he trusted was quietly lying to him. The grindstone. When Herschel plotted his counts, a shape emerged from the numbers. The star system was flattened, wide across the plane of the Milky Way and thin from top to bottom, like a lens or a grinding stone spinning in the dark. He published it in 1785, the first time anyone had drawn the shape of our galaxy from real observation rather than imagination. And there, close to the middle of that flattened disk, sat the sun. It made sense from where he stood. The band of the Milky Way looked roughly the same brightness all the way around the sky, so the natural conclusion was that we lived somewhere near its heart. For the first time, humanity had a scientific model of its home in the cosmos, a measured structure with us near the center of it all. That comfortable picture of us, sitting at the heart of everything, would survive for over a century before it collapsed. Kapteyn's universe. Decades later, a Dutch astronomer named Jacobus Kapteyn took that old counting method and gave it the rigor of modern statistics. He couldn't afford a great telescope of his own, so he did something quietly brilliant. He borrowed photographic plates from observatories around the world and studied 206 carefully chosen patches of sky, the selected areas, tallying stars by brightness and measuring how fast they drifted. From those tiny motions he could estimate distances, and from the distances he built a shape. By 1922 he had it, a flattened disk of stars about 40,000 light-years wide and 6,000 thick, thinning gently toward the edges. And there, almost dead center, sat the sun, just as Herschel had guessed 100 years before. It was the most careful map of the heavens anyone had ever drawn, built from millions of measured points of light. Kapteyn's universe was elegant, mathematical, and completely wrong, because something invisible was dimming his most distant stars. The Great Deception. Space looks empty, but it isn't. Scattered between the stars are vast, thin clouds of grains, carbon and silicate specks smaller than the smoke off a candle. Spread across thousands of light-years, they soak up starlight, like fog, swallowing a distant street lamp. The farther away a star sits, the more dust its light has to cross, so distant stars look dimmer than they really are, and a dimmer star looks like a farther one, a fainter one, or no star at all. Kapteyn had no way to know this. He measured brightness and trusted it completely, so when the star counts thinned out in every direction, he read it as the true edge of the system. But the galaxy kept going, its light just quietly erased along the way. The astronomers had mistaken the limit of their vision for the limit of the universe. Dust had convinced everyone we lived at the middle of a small cosmos, until a young astronomer found a way to see straight past it. The wrong center. Harlow Shapley wasn't looking at single stars. He was looking at globular clusters, dense spheres of hundreds of thousands of ancient stars, packed so tight they glow like fuzzy jewels. Working at Mount Wilson, with its 100-inch mirror, he found pulsing stars inside them, whose brightness ticked like a clock, and a steady beat meant a known true brightness. Compare that to how faint the star appeared, and out fell a distance. When Shapley measured cluster after cluster, the numbers were staggering. Some sat tens of thousands of light-years away, far beyond anything Kapteyn's little disk could hold. And the clusters weren't scattered evenly around us. They pooled overwhelmingly toward one region of the sky, in the direction of the constellation Sagittarius, as if drawn toward some great hidden anchor. When Shapley plotted where all those clusters gathered, the center of the galaxy turned out to be nowhere near us. Cast from the middle, Shapley ran the numbers, and the picture he drew was staggering. The sun wasn't at the heart of anything. It sat far out in a quiet suburb, tens of thousands of light-years from the true center, one ordinary star adrift in the outer lanes. And the galaxy he mapped was vast. Where earlier astronomers had imagined a modest system a few thousand light-years across, Shapley stretched it to roughly 300,000 light-years, 10 times bigger than anyone had dared to claim. He'd taken the small, tidy cosmos of his teachers and blown it wide open. It was a bold, disorienting new order, and Shapley was certain of it. But certainty is a dangerous thing in astronomy. He had made the galaxy enormous and moved us to its edge, but another astronomer was convinced he'd gone too far. The Great Debate. That astronomer was Heber Curtis, and in April of 1920, the two men met at the Smithsonian in Washington for what became known as the Great Debate. On one side, Shapley's giant galaxy, hundreds of thousands of light-years wide, containing everything there was. On the other, Curtis argued the galaxy was far smaller, maybe 30,000 light-years across, with the Sun near its middle. But the deeper fight was about the faint spiral nebulae scattered across the sky. Shapley insisted they were clouds inside our own system, part of the one galaxy that was all of creation. Curtis countered that they were separate island universes, entire galaxies in their own right, floating unimaginably far beyond our borders. Each man had evidence, and each had blind spots. Both men staked their reputations on the galaxy's size, and neither realized the answer would come from a faint smudge called Andromeda. Island universes. The answer came a few years later, through the Great Telescope on Mount Wilson in California. Edwin Hubble was photographing Andromeda, that hazy oval spiral, night after night, hunting for anything that changed. And in 1923 he found it, a single star that brightened and dimmed on a steady rhythm, a Cepheid variable. Those stars are astronomy's measuring sticks. The speed of their pulsing reveals their true brightness, and comparing that to how faint they look tells you how far away they are. When Hubble worked the math, the number was almost too large to believe. Andromeda sat nearly 1 million light-years away, far outside even Shapley's swollen galaxy. The debate was over. Andromeda was a whole other galaxy, which meant ours was just one island among billions, and astronomers still had no clear picture of what our island looked like. The spiral revealed. The more astronomers looked outward, the more familiar the view became. Beyond our own stars sat spirals by the thousand, great pinwheels of light with bright central swellings and arms curling out into the dark. If those were separate island galaxies, and one of them was Andromeda, then the obvious question hung in the air. What did ours look like from the outside? The clues stacked up. We could see a flattened band of stars, the disk we live inside. We could see stars crowding thicker toward the constellation Sagittarius, hinting at a bright central bulge. Later work would reveal a straight bar of stars cutting through that core, the signature of a barred spiral, the same design stamped on so many galaxies beyond us. So the shape was no longer a mystery in outline. We were a spiral, a disk with a bar and a bulge, one more pinwheel among billions. We finally knew our galaxy was a spiral, but the dust that fooled Kapteyn still hid its arms until astronomers learned to listen instead of look. Mapping with radio. Here's what changed everything. Hydrogen, the most common atom in the universe, gives off a faint radio signal at a wavelength of 21 centimeters into meters. It's produced when the electron in a hydrogen atom flips its spin, a rare event for any single atom, but the galaxy holds so much hydrogen that the whole disk quietly hums at that frequency. And radio waves don't care about dust. The thick clouds that blinded every optical astronomer, the clouds that shrank Kapteyn's universe, are almost transparent at 21 centimeters point, a radio dish at the plane of the galaxy, and the signal comes straight through from the far side, from regions no telescope had ever seen. So in the 1950s, astronomers began mapping that glow, tracing cold hydrogen gas clear across the disk. Slowly, the arms emerged from behind the dust, long streams of gas winding out from the center. Radio waves handed us the shape of the galaxy at last, and then they revealed how fast it was turning. A galaxy in motion, because that 21 centimeters signal carried more than shape. As the gas moved toward us or away, its wavelength stretched or squeezed, a Doppler shift, and that shift was a speedometer. For the first time, we could measure how the whole galaxy was moving, not star by star, but the entire disk at once. It was spinning, The disk turns like a vast wheel, carrying its arms, its gas, and every star along with it, our Sun included. Out here, roughly 26,000 light-years from the center, we're moving at about 220 kilometers per second, fast enough to feel impossible, yet the distances are so enormous the motion looks frozen. One full lap takes around 225 million years. The last time the Sun was in this exact spot, dinosaurs hadn't yet appeared. We've circled the galactic center only about 20 times in the Sun's entire life. The galaxy was spinning, and the way it spun should have told us exactly how much matter it contained. Oort's constants. In 1927, a young Dutch astronomer named Jan Oort took that spinning motion and turned it into arithmetic. He noticed that stars closer to the galactic center were racing ahead of us, while stars farther out lagged behind. Exactly the pattern you'd expect if the galaxy rotated like a fluid rather than a solid disk. That difference in speed, the shearing of the whole system, could be captured in two numbers. Those two numbers became known as Oort's constants. One described how fast the rotation changed with distance, the other how the local stars streamed past the Sun. Together, they let Oort estimate how quickly matter was circling the center, and from that, how much matter had to be there to hold everything in orbit. It was the first real measurement of the galaxy's pull, gravity read straight off the motion of the stars. Oort's numbers let astronomers weigh the galaxy for the first time, and the scale immediately refused to balance. Newton's prediction. To understand why that mattered, you have to know what gravity is supposed to do. Newton and Kepler had worked this out centuries earlier, watching the planets circle the Sun. The closer a planet sits to the center, the faster it moves. Mercury tears around in 88 days. Neptune takes 165 years to crawl through one lap. The rule is simple. Almost all the mass sits in the middle, so the farther out you go, the weaker the pull, and the slower you can move while still staying in orbit. Speed falls off with distance, smoothly and predictably, every time. A galaxy should behave the same way. Pack the stars and gas toward the bright, crowded center, and the outer stars, far from all that mass, ought to drift along at a fraction of the inner speed. Every law of gravity said the outer stars had to slow down, so when astronomers finally measured them, they braced for the fall. The curve that held. By the 1970s, Vera Rubin and her colleague Kent Ford had the tools to check. They aimed their spectrograph at the outer regions of nearby galaxies, measuring how fast the gas out there was actually turning. The prediction was clear. The speeds should drop the moment they left the bright central bulge behind. They didn't drop. Star after star, region after region, the outer material kept pace with the inner material, moving just as fast, thousands of light-years out, as it did near the core. Plot it on a graph, and the line that should have curved downward simply ran flat, straight across, refusing to bend. That flat line was physically impossible for the mass they could see. There wasn't nearly enough visible matter out there to whip those distant stars along that quickly. Something had to be holding them, something heavy and invisible, spread far beyond the glow. The curve refused to fall, and the only way to explain it was to invent a kind of matter no telescope had ever caught. The ghost mass. So astronomers did something bold. They accepted the numbers and let the numbers reshape the universe. If the visible stars and gas couldn't explain the speeds at the edge, then the mass had to come from somewhere the eye simply couldn't reach. They called it dark matter. Not dark like a shadow, but dark in the sense that it gives off no light at all, no radio hum, nothing. It doesn't glow, it doesn't block starlight, it just pulls. Its only signature is gravity, and gravity was screaming that it was there. And the strangest part is where they had to put it, not in the crowded core, but out in the lonely fringes, in the very region where the stars were the hardest to see and the hardest to measure. The proof lived at the edge, exactly where our evidence was thinnest. To keep the galaxy from flying apart, science conjured a ghost, and then it wrapped our entire galaxy inside it. The halo. Picture the Milky Way, you know, that bright pinwheel of 100 billion stars. roughly 100,000 light-years across. Now imagine that entire disk sitting at the center of a vast invisible sphere, a cloud of dark matter reaching far past the last visible star. This is the halo, not a flat plate like the disk, but a great rounded swell of unseen mass, and models suggested it might stretch several 100,000 light-years in every direction. The glowing part we'd been mapping for centuries could be just a small bright chip floating inside something enormously larger. The visible galaxy, all those stars and clouds and glittering arms, would be a minority. The real bulk of home would be the part you could never photograph, a silent shell surrounding everything we'd ever named. That invisible halo was supposedly the biggest part of us by far, and it made the galaxy weigh a staggering amount. Weighing a galaxy. Now, how do you actually weigh something you can't lift, can't see, and can't touch? You watch how things move around it. The faster an object orbits at a given distance, the more mass must be tucked inside that orbit, holding it in its curve. Speed and distance become a scale. So astronomers track the outermost objects they can find: distant stars, drifting gas clouds, small satellite galaxies looping the Milky Way, and they measure how quickly each one is traveling. Plug those speeds and radii into the equations, and out comes a total mass, the whole galaxy weighed in one figure. But most of that final number comes from the halo, from the far reaches where the orbits are widest and slowest. The core barely moves the total. The answer leans almost entirely on what's happening at the edge. The method was sound, but it depended entirely on stars so far out that almost no one had ever measured them. 1 trillion suns, so astronomers did the arithmetic that the flat rotation curve demanded. If stars 50,000 light-years out still orbited as fast as those closer in, the mass enclosing them had to keep climbing. Add up everything that grip implies, and you arrive at a staggering total, roughly 1 trillion times the mass of our Sun. And here's what stops you cold. The stars, the gas, the dust, everything that glows or reflects, accounts for maybe 1/10 of that. The other 90% is invisible. It gives off no light, blocks no light, and shows itself only through the pull it exerts on the things we can see. It's a number that reshaped how we picture home. The bright pinwheel we recognize turned out to be a thin decoration wrapped around something vast and unseen. 1 trillion suns became the number in every textbook, resting on a single unproven belief that the curve stayed flat forever. The cosmic web. Zoom out far enough, and our heavy dark halo stops looking like an oddity. It looks like a rule. Across the observable universe, galaxies sit inside these same swollen envelopes of unseen mass, and those envelopes aren't scattered at random. In the leading picture, dark matter formed first, collapsing into a vast network of filaments and knots long before stars existed. Ordinary gas then drained into those dense pockets and lit up as galaxies. Simulations of this cosmic web reproduce the sprawling structure we actually map, sheets and threads stretching hundreds of millions of light-years, with dark matter as the hidden scaffolding holding all of it together. By that logic, the Milky Way is one bright node in an invisible skeleton, its trillion solar masses exactly what the model orders up. The numbers matched the sky beautifully. The theory was beautiful on the largest scales, yet no one had ever tested it properly in the one place we live. Trapped inside. Because there's a problem we tend to skip past. We have never seen our own galaxy. Every photograph of a glorious spiral belongs to something else, some distant island we can view face-on from the outside. Our own we can only feel from within. We sit about 26,000 light-years from the center, embedded in the disk, staring outward through layers of stars and dust that stretch in every direction. It's like trying to map a forest while standing among the trees, or sketch a city's skyline from a single street corner at night. The nearby crowds out the distant. The flat plain hides half the sky behind itself. So every distance, every velocity, every claim about how far the edge lies had to be reconstructed from the inside, one measurement at a time. Everything we claimed about our galaxy's size came from inside it, and being trapped in the picture makes it maddeningly hard to measure. Blinded. The dust never really let go. Along the plane of the disk, clouds of gas and grains soak up starlight and redden what little gets through, so a star, sitting 20,000 light-years away on the far side of the galactic center, might as well be behind a wall. Whole spiral arms sit hidden in that murk, mapped only by the radio whispers of hydrogen that slip past the dust untouched. Then there's the crowding. Toward the core, stars pile up thousands to a single patch of sky, blurring into a wash of light where no individual point can be pinned down or measured. The outer disk has the opposite problem. Its stars are so sparse and so faint that they vanish into the background noise, scattered thin across enormous distances. And the faintest, most distant ones were the traces astronomers needed most, because they sat far enough out to feel the full pull of everything inside. The stars that mattered most for weighing the galaxy were exactly the ones the galaxy hid best. Where is the edge? So ask the simple question, where does the Milky Way actually end? Point at the sky and try to draw the line, and you find there's nothing to draw it against. The disk doesn't stop. It just thins, star by star, until the counts fade towards zero, somewhere past 50,000 light-years, with no wall, no rim, no last bright star marking the boundary. The halo makes it worse. That faint spherical cloud of ancient stars stretches out and out, growing sparser the farther you look, and stray stars wander even beyond it, some ripped from smaller galaxies the Milky Way swallowed long ago. Every definition of the edge you pick gives you a different number, and none of them feels solid. For decades, the estimates disagreed by factors of 2, 3, more. Nobody could agree where our galaxy stopped, and it turned out the edge was hiding the secret to its true size. The distance problem. Every one of those problems traces back to a single, stubborn quantity: distance. Point a telescope at a star and you get its brightness and its color, but not how far away it is. And without that one number, everything downstream collapses. You can't turn apparent brightness into true luminosity. You can't place a star in the map. You can't tell a faint nearby dwarf from a brilliant giant halfway across the galaxy. For close stars, astronomers had a clean trick, watching a star shift slightly against the background as Earth swung around the Sun. But that shift shrinks the farther out you go, until for distant stars it's smaller than the wobble of the atmosphere itself, buried in error. Beyond a few thousand light-years, distances became educated guesses stacked on guesses. As long as we couldn't measure distances precisely, the galaxy's true size stayed out of reach, and then a spacecraft was built to do nothing else. Candles and rulers. So astronomers built a ladder. The bottom rung is parallax, that tiny geometric shift we can trust only for the nearest stars. Past that, we hand off to brighter markers we can spot much farther away. The most famous are Cepheid variables, stars that pulse in a steady rhythm. Time how fast one brightens and dims, and you know its true luminosity. Compare that to how faint it looks from here, and the distance falls out. Farther still, we lean on exploding stars, the type Ia supernovae, that flare with a known brightness we can read across millions of light-years. But every rung is calibrated against the one below it. If parallax is off by a hair, the Cepheids inherit that error, and the supernovae inherit theirs. By the time you reach the far edge of the galaxy, small uncertainties have multiplied into wide margins. Each rung of the distance ladder added its own error, until one mission decided to skip the ladder and measure the sky directly. Probing the dark, distance was only half the problem. To feel the dark halo, you need something moving inside it, something whose motion betrays the pull of all that invisible mass. So astronomers reach for tracers, ordinary objects scattered through the outer galaxy that ride the gravity we can't see. Halo stars are one kind, ancient suns flung far above the disk on long, looping orbits. Stellar streams are another, the shredded remains of star clusters and dwarf galaxies stretched into glowing ribbons as the halo tears them apart. Even cold clouds of hydrogen gas drifting at the galaxy's fringe, trace the shape of the pull around them. Watch how fast these probes swing through the dark, and you can weigh what's holding them. A tracer moving quickly at great distance means more hidden mass out there, tugging hard. These distant tracers were our only handle on the dark halo, and we had pitifully few of them where it counted most. The missing sample, and that's the uncomfortable part. The grand figure, a trillion suns of mass, didn't rest on a billion measurements. It rested on maybe a few dozen tracers far enough out to matter, each one carrying error bars you could drive a truck through. Push a single one of those stars a little farther or a little closer, revise its speed by a small amount, and the estimated weight of the whole galaxy swings by hundreds of billions of suns. The sample was thin exactly where the halo does its heaviest work, in the faint, empty reaches nobody could survey well. So the number stood, quoted in textbooks and lectures, while the ground beneath it stayed soft. The heaviest claim in galactic astronomy balanced on a few dozen stars, and a billion more were about to be measured. A billion stars. In December 2013, a European spacecraft the size of a small car lifted off from a jungle spaceport in French Guiana. Its name was Gaia, and it carried no cameras pointed at planets, no instruments dreaming of alien life. It had one job, repeated more than 1 billion times over: measure where the stars are and how they move. For decades, the map of our galaxy had been stitched together from fragments, a bright star here, a rough estimate there. Gaia would replace all of it. Parked 1.5 million kilometers from Earth, it began sweeping the whole sky, logging positions and speeds for 1.8 billion stars, each one measured again and again as the mission wore on. This was the survey astronomers had waited a century for, the chance to see the galaxy's true shape from the inside. Gaia set out to chart 1 billion stars with impossible precision, and buried in that flood was a number that shouldn't have existed. The precision machine. To pull this off, Gaia never stops moving. It spins slowly on its axis, one full turn every 6 hours, while that spin axis itself sweeps a wide circle across the sky. 2 telescopes stare out at a fixed angle apart, feeding their light onto a single billion-pixel camera, the largest ever flown into space. As stars drift across that sensor, Gaia clocks their positions to a staggering degree of fineness. We're talking angles measured in micro-arc seconds, small enough to spot a coin sitting on the moon, or a human hair seen from more than 1,000 kilometers away. Nothing built by human hands had ever pinned down the sky this tightly. And it does this not for a handful of chosen targets, but for the entire vault of the heavens, one careful pass at a time. Gaia's precision was almost unbelievable, and it aimed that precision straight at the galaxy's faint, distant rim. Parallax. That precision unlocked the oldest trick in astronomy, done right at last. Parallax. Hold up a finger and blink one eye, then the other, and it seems to jump against the background. Stars do the same tiny dance as Earth swings from one side of its orbit to the other, and the size of that shift tells you, directly, how far away they are. No assumptions about brightness, no borrowed rungs on a shaky distance ladder, just geometry, the same math a surveyor uses, applied to the sky. For close stars, the shift is easy, but Gaia's steadiness let it catch that faint wobble for stars thousands of light years out, where every earlier method had turned to guesswork. Suddenly, the distances weren't estimates layered on estimates. They were measured, clean, and trusted. With true distances in hand, astronomers could finally measure how fast the outer galaxy was really turning. Charting the rim. For most of history, the outer disk was a rumor. A handful of stars out there, each with a distance you had to argue about, none of them quite trustworthy on their own. Then Gaia turned that emptiness into a census. Suddenly, the galaxy's far reaches held thousands of stars with distances good to a few percent, their motions tracked across the sky year after year. Ground surveys like Apogee and Lamost filled in the chemistry and the line-of-sight speeds, so each point on the map carried both position and velocity. Stars 40,000, 50,000, even 60,000 light-years from the center stopped being guesses and became data. You could watch them wheel around the disk, one by one, and start to see how the whole outer wheel was turning. For the first time, we had a crowd of stars at the galaxy's edge, and their motion was about to break the trillion-sun story. Into the halo. The disk was only the beginning. Beyond it lies the halo, a vast, thin sphere of ancient stars scattered far past where the spiral arms fade. These stars are faint and few, but they wander out to distances the disk never reaches, 80,000, 100,000 light-years and more. Astronomers went hunting for them, and for something even better, stellar streams. When a small galaxy or a globular cluster falls in and gets torn apart, it leaves a long ribbon of stars strung along its old orbit. Trace that ribbon, and you're reading the shape of gravity itself at the outer edge. Gaia caught these streams and halo stars in motion, tracking how fast they drifted through space at distances no rotation measurement had ever reached. Each one was a test mass falling through the galaxy's pull. The farther out they measured, the stranger the numbers became, as if the galaxy's grip was weaker than anyone dared say. Clocking the spin. So the teams built the rotation curve properly this time. Not a few nearby points, but a continuous line stretching from the Sun's orbit at 27,000 light-years out to the ragged edge of the disk. Every point rested on a real distance and a real velocity from Gaia, not a model stacked on assumptions. Inside the Sun's orbit, the curve behaved the way textbooks promised, staying flat, holding near 230 kilometers per second, exactly the signature that once demanded oceans of dark matter. The interesting part was always going to be the far end, where the disk thins and the stars run out. That's where the numbers had to prove themselves, where the halo's true weight would either confirm the old story or quietly contradict it. As the measurements marched outward, the curve started to do the one thing dark matter said it never could. The first dip, out past the Sun's orbit, somewhere beyond 15 kiloparsecs from the center, the numbers started to slip. Not by much. A few kilometers per second here, a handful there, the kind of drift you'd normally blame on a noisy measurement or a bad night of data. But this drift didn't wander. It leaned in one direction, always downward, always at the same distant reaches where the disk fades and the last bright stars thin into darkness. The flat line that textbooks had drawn for decades was starting to sag at its very tip. For a while it was easy to look away. A single dip in a sea of data points is the sort of thing careful astronomers are trained to distrust. And yet it kept showing up, faint but stubborn, in exactly the place where dark matter had promised the speeds would never fall. The curve had begun to fall, and now everything hinged on whether that dip was a mistake or a message. The curve turns, so they went back to the stars themselves, tens of thousands of them, red giants scattered across the outer disk, each one's motion measured and remeasured, its distance pinned down and checked against the next. If the dip was an artifact, more data should have washed it out. It didn't. The more stars they folded in, the sharper the downturn became. Points that had looked like scatter began to line up along a slope, and that slope pointed down. By the outer edge, the rotation speed wasn't holding near 220 kilometers per second the way the flat model demanded. It was measurably lower, and it kept dropping the farther out they looked. A flat curve is a straight promise that mass keeps piling up with distance. A bending curve breaks that promise. The downturn was real, and this is where the story of our galaxy takes a turn no one had planned for. Falling away. Think about what a falling curve actually means. When a planet orbits far from the Sun, its speed drops off in a smooth, predictable way, because almost all the mass sits behind it, near the center. Newton wrote that down centuries ago. Orbital speed fades with distance when there's nothing more out there to pull on you. That's the shape the Milky Way's edge was starting to trace. Not the eternal flatness of a galaxy wrapped in endless invisible mass, but a decline bending back toward the old Keplerian fall-off, the curve of a system that's mostly already behind you. If the speeds drop that steeply, the arithmetic is unforgiving. Less rotation at the rim means less gravity gripping those distant stars, and less gravity means less mass out there doing the gripping. The great dark halo that was supposed to stretch on and on had to be lighter than anyone had drawn it. The curve was falling the way gravity always said it should, which meant the galaxy was hiding far less mass than we'd ever claimed. The missing dark matter. Think about what a rotation curve actually traces. Every star's speed tells you how much mass sits inside its orbit, tugging it around. When those speeds keep climbing outward, you're forced to keep adding invisible weight to explain the pull. But when the speeds start dropping, the math runs the other way, and you stop adding mass because there's simply less of it left to account for. So a falling curve isn't just a slower spin, it's a signal that the dark halo thins out and runs dry far sooner than the old models allowed. Those models leaned on a halo that kept feeding gravity outward for hundreds of thousands of light years, holding roughly 1 trillion suns worth of unseen matter in place. Gaia's stars were whispering a different number, and it was smaller than anyone wanted to believe. If the halo really ended that soon, then the galaxy's official weight had been wildly overcounted, and the correction was brutal. 5 times lighter. When researchers folded the new speeds into their equations, the totals came back shockingly light. Several Gaia-era studies landed the Milky Way's mass somewhere near 700 billion to 800 billion suns, and some pushed lower still. That's a long way from the tidy trillion or more we'd been quoting for decades. Depending on which distant traces you trust and how far out you dare to measure, the figure can fall to a fraction of the old estimate. Not a modest trim, not a rounding error. In some accounts, the galaxy comes out several times lighter than the number in the textbooks. A whole galaxy, the one we live inside, quietly reweighed to a sliver of its assumed heft. Our galaxy may weigh a fraction of what we were taught, and that single fact changes where we stand in the cosmic order. The shrinking halo. Less mass doesn't just change a line in a table, it reaches into the halo itself, the vast sphere of dark matter that was supposed to wrap the galaxy in an enormous, faint cocoon. Lighter total, smaller halo, and the edge of our gravitational reach pulls inward toward us. For years, the picture was a sprawling dark shell, reaching out maybe 900,000 light-years, its grip loose but enormous, claiming space far beyond the stars. Trim the mass, and that boundary contracts. The territory where the Milky Way's gravity truly rules turns out to be tighter, more contained, less of a giant's domain than we'd drawn. It's an unsettling revision because that halo was part of how we imagined ourselves, sitting at the center of something immense. The invisible halo we thought stretched forever appears to end far closer in, and that quietly shrinks the whole galaxy. Not the heavyweight. For decades, the number sat comfortably in textbooks. Roughly 1 trillion solar masses, the Milky Way as a heavyweight, one of the more imposing spiral galaxies in the local universe. It was a figure we quoted with a certain pride, the kind of scale that made our home feel important. The newer measurements don't cut it in half. They cut it to something closer to 1/5 of that older estimate, somewhere in the range of a few 100 billion solar masses once the outer halo is properly weighed. That's not a rounding error. That's a different galaxy wearing the same name. And the strange part is how ordinary it makes us look. Not the dominant giant of some grand cosmic story, just a respectable spiral among many, sturdy but far from record-setting. We had always pictured ourselves as one of the big ones, and the new numbers were about to introduce us to our real rival. A smaller Milky Way, so the portrait gets redrawn line by line. A galaxy with less mass than a century of teaching implied, wrapped in a halo that's more modest than the endless cloud we'd sketched, edged by a boundary that sits far closer than we let ourselves believe. The stars don't change. The 100 to 400 billion suns are still there. the spiral arms still turning through the same 225 million year rotation. What changes is the dark scaffolding around them, the unseen mass that was supposed to make us formidable, and it simply weighs less than we counted on. There's something quietly humbling in that. The galaxy you were born into is the same one it always was, but the story we told about its heft, its reach, its place in the pecking order, that story was too generous. A smaller, lighter galaxy raised an uncomfortable question about the neighbor we'd always assumed we matched. The Andromeda reversal. Andromeda has always been the twin in the mirror. Same spiral shape, same rough size on the sky, the other anchor of our local group, and for years the assumption held that the two of us were near equals, two giants circling toward an eventual meeting. But if the Milky Way now weighs a few 100 billion solar masses and Andromeda's measurements hold nearer to 1 trillion, the symmetry breaks. The mirror was flattering us. Andromeda may not be our twin at all, but the clearly heavier partner in this pairing, the one that sets the terms. It's an odd thing to discover about a galaxy we've stared at for centuries, that we misjudged not just our own weight, but our rank beside it. If Andromeda outweighs us more than we thought, then the balance of power in our corner of the universe just flipped. Rebalancing the group. Change the weight of the Milky Way, and you don't just change one galaxy, you change the arithmetic of the whole neighborhood. The local group is a small crowd of galaxies bound together by gravity, and for decades, the Milky Way and Andromeda were treated as the two anchors holding roughly equal shares of the mass. Trim our galaxy down, and that shared load shifts onto Andromeda's side of the ledger. The numbers matter because they set how everything moves, the speed at which the two giants drift toward each other, the paths of the dozens of dwarf galaxies orbiting between them, the total mass astronomers use to weigh the group as a whole. All of it leans on what the Milky Way actually weighs. A smaller value ripples outward through every one of those calculations. It even touches how the group formed, how much dark matter it needed to pull itself together in the early universe. A lighter home galaxy reshuffles everything around us, but a claim this big was never going to go unchallenged. Doubts. Plenty of astronomers looked at the declining curve and weren't convinced. Their objection was simple. The fall-off shows up in the outer galaxy, tens of thousands of light-years from the center, and that's exactly where the data gets thin, noisy, and hard to trust. Out there, you're tracking a scattered handful of stars, not the dense, well-measured population near the disk. If your sample is patchy, or if a few of those stars aren't behaving the way you assume, the whole curve can bend the wrong way. What looks like a real drop in speed might just be scatter dressed up as a trend. There were deeper worries too. Maybe the stars used to trace the rotation weren't on clean circular orbits. Maybe the model quietly built in the very result it produced. Critics argued the falling curve might be an illusion, and the only way to answer them was to hunt down every possible source of error. Sources of error. So the objections got tested one at a time. Start with the disk itself, which isn't a flat plate. The outer Milky Way warps and flares like the brim of a hat, and if you ignore that bend, you misplace stars and misread their motion. So the models put the warp back in and looked again. Then the orbits. Stars don't all circle in tidy rings. They drift, they wobble, they follow streams left over from swallowed galaxies, and those non-circular motions can fake a rise or a fall. Researchers filtered for them and remeasured. They checked whether the sample simply ran out of stars too soon, and whether the assumptions about the galaxy's shape were quietly steering the answer. Each doubt was examined and weighed, and one by one they failed to make the falling curve disappear. The curve confirmed. Then other teams took their own paths to the same place. Using the second Gaia data release, and later the far richer third, independent groups rebuilt the rotation curve from scratch with different stars and different methods. The line kept sloping downward past 20 kiloparsecs, dropping by roughly 30 kilometers per second across the outer disk. That agreement mattered. When separate researchers, working with fresh data and their own assumptions, land on the same falling curve, a single team's mistake stops being a plausible explanation. The decline wasn't an artifact of one pipeline or one clever choice. It was written into the motions of millions of stars. So the wobble hardened into a result, and the result pointed one direction. Our galaxy simply doesn't hold as much matter as the old flat curve models demanded. The decline held up under every test, and now astronomers had to explain how a galaxy this light came to exist at all. A new history. Mass is a galaxy's biography. How much a galaxy weighs today tells you how much it pulled in over billions of years, how deep its gravitational well ran, and how greedily it fed on everything around it. Lower the number, and you're not just changing a figure in a table, you're rewriting the whole life story. A heavier Milky Way needed a busy, dramatic youth, growing fat by dragging in gas and smaller galaxies again and again. A lighter one suggests something quieter unfolded across cosmic time. Less pull, a shallower well, a more modest appetite for the matter drifting nearby. And that reshapes the timeline of how we came to be here. Every model of the disk, the halo, the slow assembly of our home was tuned to a galaxy that now looks too big. A lighter galaxy demands a gentler past, and that means fewer of the violent collisions we'd blamed for building it. Fewer collisions. Big galaxies grow by eating. In the standard picture, the Milky Way spent billions of years swallowing dwarf galaxies, tearing them apart and stitching their stars into its halo. A more massive galaxy has stronger gravity, a wider reach, and pulls in more of these smaller neighbors over its lifetime. Shrink the mass, and you shrink the reach. A lighter Milky Way would have captured fewer of those passing dwarfs and swallowed them less often. The tally of mergers we'd assumed built us starts to shrink along with the number on the scale. That points toward a calmer accretion history than the textbooks describe. Fewer collisions, gentler encounters, a galaxy assembled with less violence than we'd pictured. But a quiet past leaves its own mark. If we ate less than we thought, then the calm, orderly disk around us starts to look surprisingly fragile. The fragile spiral. A spiral disk is a balancing act. The stars and gas that make our galaxy's flat, sweeping arms are held in check by the gravity of the dark matter around them, and that halo acts like a stabilizing frame. Take mass out of the frame, and the frame loosens. With a lighter halo, the disk sits in a shallower gravitational well. It's easier to warp, easier to disturb, more responsive to anything that passes close enough to tug on it. The delicate structure that carries our solar system around the center every 230 million years starts to look less like something anchored and more like something poised. That fragility changes how we think about the future, not just the past. A disk that reacts more sharply to gravity is a disk more easily reshaped by whatever comes next, and a more fragile galaxy raises the stakes for the one event we've always known was coming for us. The collision rewritten. For years, the forecast felt settled. Andromeda, racing toward us at about 110 kilometers per second, would slam into the Milky Way in roughly 4 billion years, and the two spirals would tear each other apart and merge into a single elliptical blur. It was written as fact, a date circled on the cosmic calendar. But that certainty leaned on knowing both galaxies' masses and their exact sideways motion. Lower the Milky Way's weight, and the gravitational pull drawing the two together weakens. Add sharper measurements of Andromeda's transverse drift, the slight sideways drift that decides whether two galaxies hit head-on or merely graze past, and the collision stops being guaranteed. Recent studies now put the odds of a direct merger within the next 10 billion years at closer to 50%. A near miss becomes just as likely as a crash. Even our inevitable collision with Andromeda is no longer certain, and that forces a quieter, more personal question. A smaller home. We keep learning we're smaller than we assumed. Earth was moved from the center of everything. The sun became one ordinary star among hundreds of billions. Our galaxy, we told ourselves, was at least a heavyweight, one of the grand spirals of the local group. Now even that consolation loosens its grip. A lighter Milky Way is a more modest home, its reach shorter, its gravity gentler, its story less violent than the epic we'd written for it. There's something humbling in trading grandeur for accuracy, in seeing the place you live measured down to its true size. But the sting carries a question underneath it. If we've been overcounting the mass of our own galaxy, the one we can study more closely than any other, then losing our place as a giant raises the possibility that we've been overweighing galaxies across the whole universe. Are we unique? So the natural question is whether the Milky Way is the odd one out. Maybe we live in a galaxy that runs unusually light, a quiet exception in a universe of heavier spirals. That would be reassuring in a way, because it would leave every other measurement standing. But the tools we use to weigh our galaxy aren't special to us. We watch how fast stars orbit, we track the drift of satellite galaxies, we model the pull of the halo we can't see. Those same methods, the same assumptions, get pointed at galaxies millions of light-years away, where we can't check the details half as well. And that's the uncomfortable part. We didn't overcount our own mass because the Milky Way is strange. We overcounted because of how we counted. If our galaxy was overweighed, the same mistake might be hiding in every galaxy we've ever measured. The Great Recount. Follow that thread and it doesn't stay small for long. When you weigh a galaxy, most of what you're weighing isn't the stars at all. The visible matter, the suns and gas and dust, makes up only a fraction. The rest is inferred, the invisible mass we call dark matter, calculated from motion we can see, but a source we can't. So trimming a galaxy's total mass doesn't trim the stars. It trims the dark matter we assumed was holding everything together. Shave a little from one spiral, and it's a curiosity. Shave it from a whole population of galaxies, systematically, and you're rewriting how much unseen material the cosmos contains. Every large structure we've mapped, every cluster, every thread of the cosmic web, was built on those weights. Change the galaxies, and you nudge the scaffolding of everything above them. A recount of galactic mass on this scale reaches all the way up to the ledger of dark matter itself. The dark matter census. Now this doesn't mean dark matter vanishes. A lighter Milky Way still spins far too fast for its visible stars to explain. Something unseen is still there, still pulling. The evidence for dark matter never rested on one galaxy's exact weight. What shifts is our confidence in the numbers. Dark matter, as an idea, survives comfortably. But the census, the precise tally of how much there is and where it sits, starts to look softer than we'd like. If our best-studied galaxy was off, the ones we can barely resolve carry error bars we may have been quietly ignoring. That's the quiet discomfort underneath all of this. The theory holds, but the bookkeeping wobbles. Our galaxy's diet doesn't kill dark matter, but it does force us to ask how confidently we've weighed anything at all. Weighing the universe. Step back far enough, and one galaxy's mass is a single data point in a much larger accounting problem. To weigh a cluster like Coma, astronomers watch how fast its galaxies swarm, then infer the gravity needed to hold them together. That trick, first tried by Fritz Zwicky in the 1930s, is what revealed the missing mass we now call dark matter. Zoom out again, and the galaxies themselves are just knots in the cosmic web, filaments of matter stretching hundreds of millions of light-years between vast empty voids. We weigh those structures by how they bend light, by how they cluster, by how the whole scaffold grew over 13 billion years. Each method leans on the one below it, and every rung inherits the wobble of the rung beneath. So when the Milky Way's number shifts, it nudges the calibration of everything stacked above it. Weighing the universe turns out to be as humbling as weighing our own galaxy, and the scales are still moving. The edge of knowing. Look back through the last century, and the galaxy kept refusing to sit still. In the 1920s, Harlow Shapley pushed the Sun out of the center and made the Milky Way suddenly enormous. Then Edwin Hubble showed those faint spirals were other galaxies entirely, and our home shrank back into one island among billions. Each generation measured with the best tools it had and felt sure the picture was settled. Radio astronomers mapped the spiral arms in the 1950s. Rotation curves in the 1970s hinted at far more mass than anyone could see. Every advance answered one question and quietly opened three more. That's the pattern worth sitting with. Better light, better parallax, better patience, and the old certainty gives way. Every era thought it had the galaxy pinned down, and every era was corrected, which means our smaller Milky Way is only the current answer. The map unfinished, and the measuring hasn't stopped. Gaia has now charted the precise motions of nearly 2 billion stars, and each fresh data release sharpens the outer rotation curve that sets the galaxy's weight. Every star it tracks is another tiny lever on the total mass. Beyond Gaia, new eyes are opening. The Vera Rubin Observatory in Chile will image the entire southern sky every few nights, catching the faint, far-flung stars and streams that trace the dark halo's edge. Missions built to map dark matter across the wider cosmos will feed straight back into how we weigh our own neighborhood. None of these will hand us a final number, and that's the quiet promise of it. The map of our galaxy is still being redrawn as we speak, and what comes next may shrink us further still. The revised sky. We opened this journey trusting a familiar number, 1,000,000,000,000 suns, give or take, packed into the great pinwheel we call home. It's the figure printed in textbooks, quoted in classrooms, the weight of a galaxy that seemed too vast to ever feel small. Then Gaia measured the way our outer stars actually move, and the number buckled. The mass held in the Milky Way's grip may be closer to a fifth of what we assumed, a galaxy perhaps 5 times lighter than the heavyweight we drew for a century. The spiral didn't shrink in the sky. Our confidence in its heft did. There's a strange comedy in it. For decades we sharpened our instruments to weigh distant galaxies, certain we understood the scale beneath our own feet. But if the ruler we trusted for the Milky Way was wrong, that same ruler had already been laid across every galaxy we ever weighed. Still inside, and that's the part that unsettles. Every measurement we've talked through was taken from the inside, by observers sitting roughly 26,000 light-years from the center of the very thing they're trying to weigh. We can't step back and see the Milky Way whole. We infer its edges from the motion of stars we can barely track. So even this smaller galaxy isn't a verdict. It's the best reading we have, built from Gaia's orbits and the faint tug of dark matter we still can't touch. Change the assumptions about that halo, and the number shifts again. We are cartographers, mapping a country while standing in one of its fields at midnight. The next instrument could confirm the lighter Milky Way or push it somewhere we haven't imagined yet. But whatever the final number turns out to be, it presses a quieter question no telescope can answer. What does a smaller galaxy make of the ones who call it home? A smaller place. For as long as we've had the words, home has been the giant of the local group, the anchor that Andromeda would one day meet as an equal. A lighter Milky Way rewrites that standing. We're no longer the settled heavyweight of our own small cluster of galaxies, just one member whose true weight is still being argued over. There's something tender in learning your home is more fragile than you thought. Not diminished exactly, but less certain of its own size. The spiral still turns. The sun still carries us around it once every 230 million years or so, and somehow it all feels more precious for being lighter than we swore it was. We wanted the cosmos to hold still long enough to be measured, and instead it keeps handing back smaller answers. But smaller is not the same as settled, and the very measurement that shrank our galaxy is being refined again tonight. The weight of home. Think about what one falling curve did. The rotation speed dipped where it should have stayed flat, and that single downward slope pulled the Milky Way down with it, from 1,000,000,000,000 suns of implied mass towards something closer to a fifth of that, roughly 200 billion. A galaxy we called a heavyweight turned out to carry a lighter halo, a smaller reach, a thinner cloak of dark matter than the old models demanded. Andromeda kept its bulk, while ours quietly stepped down, and the balance of the whole local group tilted with it. The stars didn't move, the spiral didn't shrink. What changed was us, catching the galaxy in a more honest light, watching 1.8 billion stars trace an arc that finally bent the way gravity said it should. So we live somewhere gentler than we imagined, a modest spiral turning in a crowded cosmos, its true weight still being tallied star by star. As of 2024, that count is far from over. This story isn't finished, not even close.